In this video, we are going to continue talking about the concepts of Chapter 2. Now, we are going to be discussing acids, bases, and pH. Understand that the behavior of many important compounds in biochemistry is influenced by their acid-base properties. There are many definitions for acids and bases, but primarily in biochemistry, what we are going to be utilizing is the Bronsted-Lowry definition for acids and bases. When it comes to an acid, understand that an acid is going to be a molecule that is going to donate a proton, while a base is going to be a molecule that accepts the proton that has been donated by the acid. Now, if we look at the example that we have in the top left corner of the slides, we see that we have two molecules on the reactant side of the reaction. We have hydrogen chloride, or hydrochloric acid in other words, in water. Now, we can observe here that the HCl is going to be acting as an acid, while the water is going to be acting as a base. What that means is that when we have the product of the reaction, we are going to be creating two species. Specifically, you can see that the conjugate base, the reason why it is also in red is because it is the molecule that is formed after the acid has donated the proton. And in this case, that conjugate base specifically is going to be the chloride ion. We also have in this system a conjugate acid. And the conjugate acid is related to the base because it's the molecule that it results from the base accepting the proton from the acid. And in this reaction, you can see that the hydronium ion is going to be the conjugate acid of the water molecule in this reaction. Now, in this chapter, we're focusing on water. One particular thing that water can do is that we saw in the previous example how water acted as a base, which is the first part of this slide. But water is known as an amphoteric molecule. Amphoteric just means that water not only can act as a base, but it can also act as an acid. So the example that we have when water acts as a base, it was the one that was described in the previous slide. But when water acts as an acid, as you can see, water, specifically in the presence of a weak base, like ammonia, what it's going to do is that it's going to be donating a proton. So that means that we are going to form ammonium, which is the conjugate acid, of the system, and we're going to form hydroxide, which is the conjugate base of the system. Now, this is very important because this characteristic of water being amphoteric actually give us an understanding of Kw. So Kw is going to be specifically the dissociation constant for water specifically. Now, as we can see in the following slide, we know that the dissociation constant, which is Ka is going to be pretty much for any acid. Kw is basically for water. It's going to be a measure of the extent of the dissociation of an acid, okay? So understand that when we have specifically a weak acid that is designated by the letters capital H and capital A, and we put it in water, what is going to be happening overall is that that weak acid is going to create its conjugate base and hydronium will be formed. So the Ka, understand, because this is dissociation constant, when we write it, is going to be the concentrations of the products on top divided by the concentration of the reactants. The only thing is that you see that the term for water, it is not included in the equation because water is going to have a constant composition. So in general, when you have the Ka, understand that is going to be the concentration of the hydronium times the concentration of A minus, in other words, the conjugate base, everything divided by the concentration of the weak acid. In general, for this course, you guys don't need to know how to do those calculations. What you need to understand is the trend, that something that has a large Ka is going to be a strong acid. Because if you think about it, when it comes to this, what's going to happen is that if it's a strong acid, we're going to have more of the top components compared to the concentration of the acid itself. So it just makes sense that a larger Ka corresponds to a stronger acid. When it comes to biochemistry, understand that most of the acids that we are going to be dealing with are going to be weak, okay? And when it comes to how do we relate that Ka terms in order to be looking at values, well, we are going to be mainly focusing on the term pKa. Understand that pKa is a convenient numerical measure of the of acid strength. The lower the value of pKa, that it indicates that the acid is going to be more willing to dissociate, meaning giving away that proton in water. How do we calculate the pKa? As you can see, is going to be a logarithmic scale given by the equation in the second bullet point, in which you have the negative log base 10 of that Ka term. To give you some examples of pKa's, we see in the table in the slide that is on the right side terminology for example, acids that are commonly used in chemistry. So as you can see, starting from the bottom where we have hydroiodic acid, hydrobromic acid, here they're just named as hydrogen iodide or hydrogen bromide. You see that at the bottom, we are going to have the stronger acids. So in the bottom, the values that are negative, these are going to be the strongest acids. And then the strength reduces as it moves up. So as we're moving up, it's getting weaker. So remember, in terms of these numbers, this just means that the compounds that we have towards the top are going to be less willing to lose a proton in water. Now, this terminology of pK, it is very useful because when we are dealing with molecules, we want to see how willing is a particular proton willing to leave a system. But there is another scale that it is known that also gives us an insight into the acidity, but in terms, it actually gives us also an overview of the basicity of the system, and that is the pH scale. So when it comes to the pH scale, understand that this is a measurement that not only looks at acids, but it actually looks at bases, okay? So it tells you how acidic or basic a solution is. When it comes to the pH scale, understand that the pH scale is also a logarithmic scale. And the equation, as you can see here, is given in the bottom, which states that the pH equals to the negative log base 10 of the concentration of H plus. What does this mean? That when we're talking about pH, pH specifically looks at concentrations of protons. And remember that pKa looks specifically at the willingness of losing protons. Now, The reason why the pH scale also gives us insights about the basicity is because remember that when you are under basic conditions, the concentration of protons is going to be less compared to when we are under acidic conditions. Now, when calculations need to happen to understand how much protons you have in the system or how much hydroxide ions you have in the system, understand that they are all given by the equations that are in this flow chart. So understand that you should be familiar with all of these equations, which have been presented to you in the past in other chemistry classes. But we're going to practice with some book problems on some of the things that you need to know. But understand that all of the equations given in this diagram that is to the right of this slide are necessary for you to know for the exam. Let's proceed to the next question. As you can see, we're going to try the book problem, which is problem 23 and 25. On problem 23 and 25, they're related to one another because it says, calculate the hydrogen ion concentration, H plus, in other words, the proton concentration and the hydroxide concentration for each of the following materials. And as you can see here, we only have the pH levels for these substances. So as you can see, the first one that we have is blood plasma. So what I'm going to be doing is working out the problems for blood plasma, but then the procedures that I utilize are also going to be used for human urine and household ammonia. Make sure that you practice at home the results for the second bullet point and the third one. So let's get started with blood plasma. So blood plasma has a pH of 7.4. In the problem, we need to find the concentration of protons, and also we need to find the concentration of hydroxide. There's different ways that you could do this, and they should get you to the results that are very similar. Understand that in this class, we are not going to be focusing so much on the significant figures. So understand that as long as you can round your answer to 2 decimal places, you are getting close enough to the answer. So in a case where you're given pH, if we look at the equations that were given before, we can directly find concentration of H plus, because concentration of H plus is actually the equation that we're going to utilize is 10 to the negative pH. So if you raise to the negative pH the 10th power, that will give you the concentration of H plus. So if we put this in our calculator and we do 7.4 negative and we raise it to the power 10, that is going to give us a value of 3.98 times 10 to the negative 8. And remember, because its concentration is going to be molar. Okay? Now, at this pH, when we are trying to find the concentration of OH minus, there's different ways that we could do this. So, for finding the concentration of OH, you could do the following technique. Okay? You can say, well, I know that my concentration of H plus, when I multiply it times the concentration of hydroxide, that is going to equal 1.0 times 10 to the negative 14 molar. And that equation, again, comes from the idea that when you multiply the concentrations of proton and hydroxide ions, it's going to be constant at 1.0 times 10 to the negative 14 molar. So taking this into account, and because in the first part of the equation you already calculated how much proton concentration we have, to find OH, you can say the concentration of OH is going to be 1.0 times 10 to the negative 14 molar divided by 3.98 times 10 to the negative 8 molar. And when we do this, 1 times 10 to the negative 14 divided by 3.98 times 10 to the negative 8, we get a value of 2.51 times 10 to the negative 7 molar. That's one way that you can solve it. Of course, you can utilize the POH equation and then take 10 to the negative POH to solve it. There's many ways to solve it, but I just selected to do this one. Now, why is it so important that we talk about pH when we're talking about biochemistry? That is because some biochemical reactions cannot take place if the pH varies from the optimum value. So understand that many of the reactions that happen in biochemistry are driven by the utilization or the use of enzymes. So enzymes are biomolecules that act as catalysts. So a catalyst, just like you've learned in other chemistry classes, are going to be a particular molecule. In case of biochemistry, it's going to be called an enzyme that is going to speed up the reaction to get to product. Now, when it comes to enzymes in biochemistry, understand that they have what is called a optimum pH. So what that means is that that optimum pH is where the enzyme is going to have the highest activity. What I want to illustrate with the graph that you see in the top right corner of the slide is that the enzymes in biochemistry not all have to work at the same pH of 7.4, which is the pH of the blood. Depending on the location of the enzyme, each of them will have their own pH. So to give you an example, if we look at pepsin specifically, this enzyme, its optimum pH is around pH 2. While here, where we have trypsin, and we're going to talk about these enzymes later and what they do in the body, its optimum pH is around 7. If we look at lysozyme, and just to give you an insight, all of these enzymes are going to be involved in hydrolysis of different bonds. The optimum pH is around 5. As you can see, it doesn't matter if we are going to be increasing in pH, for example, in the cases that the graph is illustrating it, like in trypsin and lysozyme, if we have a big increase in pH or if we lower the pH, the activity decreases. But just understand that the reason why it is important for us to understand pHs in biochemistry is because the biomolecules that are the ones in charge of the reactions will lose activity. Now, understand that because it is important to understand pH and to understand the ability for a molecule to dissociate or to basically be willing to donate a proton, there is an equation that is going to connect the Ka of a weak acid with the pH of the solution, okay, that contains acid and its conjugate base. That equation specifically is known as the Henderson-Hasselbach equation. As you can see overall in this equation, this mathematical relationship, it relates the pH of a solution with the pKa of an acid, and it also shows the ratio of acid and conjugate base in the solution. This equation is also known as the buffer equation. In this buffer equation, understand that is going to be very useful in predicting the properties of buffer solutions that are used to control the pH in reaction mixtures. Because one of the things about biochemistry is that since we know that our enzymes require a pH, we need to have them in an environment when they are studied outside of the body that doesn't have big fluctuations in pH, because that can affect the overall activity. Now, in the textbook, there are different problems dealing with specifically the Henderson-Hasselbach equation. To give you an example of the problems that I expect you guys to know for the exam, I'm going to work out problem 37 from the textbook. As you can see, it says, calculate the pH of a buffer solution that is prepared by mixing 75 milliliters of a 1.0 molar lactic acid and 25 milliliters of a 1.0 lactate. So, in order to utilize the Henderson-Hasselbach equation, we always need to have specifically the pKa of our weak acid, which in this case is going to be lactic acid. Now, let's rewrite the Henderson-Hasselbach equation, which states that pH equals pKa plus the log of the conjugate base divided by the weak acid. In this case, lactic acid is going to be our weak acid. Lactate is going to be its conjugate base. Because remember, lactic acid is going to be a carboxylic acid. We can determine that from the name. The one that ends in H is going to be the carboxylate. Now, when we look at what are the concentrations specifically, because in these buffer solutions, we are combining specifically a certain amount of one versus the other, we can utilize the dilution equation to understand how much do we have. So, if we think about it, in this system, to understand what is going to be our concentration of HA, we can utilize the dilution equation saying that we have 75 milliliters of a concentration of 1.0 molar of lactic acid. And we know that when we do 25 milliliters plus 25 milliliters, that's going to be 100 milliliters that we have overall in the solution. And we're trying to define what is going to be our final concentration. So that's going to be what we're trying to find. So overall, understand that if I say 75 milliliters times 1.0 molar divided by 100 milliliters, the milliliters cancel. So when I do this, my concentration is going to be 0.75 molar for my HA. I can do a similar equation for my concentration of A minus of lactate. I can say 25 milliliters of that 1.0 molar lactate equals 100 milliliters, and I'm trying to find that question mark. So overall, when I say 25 milliliters times 1.0 molar divided by 100 milliliters, then my concentration of A minus is going to be 0.25 molar. Now that I have the concentrations for each one of my weak acid and for its conjugate base, then I can plug it into the equation, okay? So the pH of this buffer solution is going to be 3.87 or 2.86 plus the log of taking 0.25 molar divided by 0.75 molar. So when I plug this in, I'm going to take 3.86 subtracted from 0.48, 3.86 subtracted from 0.8. The pH of this solution is going to be 3.38.